So I did upload these slides, this PDF of slides, to your Blackboard under Lectures and Notes, or Lectures and Code. So we got some stack and a queue going on there. All right, a different kind of data structure. Okay, last time we learned about linked lists and we learned about what an ADT is. Today we're going to learn about stacks and queues. And stacks and queues are also an abstract data type. That's why they're usually kind of lumped together. All right. And stacks and queues are more programmers' tools. Okay, usually you're not going to use a stack or a queue when you're creating a program to store all of the rain data in Merced and sort it. Okay, you're not going to sort data inside of a stack and a queue. Okay, they're not for sorting. They're not for finding things. You know, they're just for storing things in a place, you know, a temporary data holding area, rather than a structure to hold all of your program's data. Okay, so they're more like a programmer's tool. They're used a lot in real life. They're used in your compiler. Okay, we're going to actually make part of a compiler today. We'll make a parser today. Okay. They're usually created, used, and then discarded by your program. In fact, you guys have come in contact with the stack all the time when you're compiling things, and then a stack overflow error in your quicksort, right? Yeah, so your quicksort used recursion, right? And so every time something is recursed, all of that method's variables and data get pushed on what's called a stack. And when the stack is full is when you have a stack overflow error. So your stack for your compiler is only so big. So that's, you know, you came in contact with your stack when you get those stack overflow errors. All right. Access to items in these kind of data structures are restricted. You can't find things in this data structure. You only can insert and get things out a certain way. And that's what makes them what they are. Okay. And all right, let's go next. So a stack and a queue is abstract because it's an abstract data type, and it's abstract in that it is defined by the operations that can be performed on the data structure and not how you implement it. Remember, that's what an abstract data type is. Okay, it's what that data structure does and how it works, and not how you created it, not how you wrote the code, not how you implemented it. When I say implement it, that means writing the actual code. Okay, you can implement a stack and a queue with an array. You can implement it with nodes. You can implement it with, you can actually implement a queue with a stack. Okay, that used to be one of my in-class assignments. We would implement the queue with a stack. Okay. So how you actually store the data is unimportant. It's how the rules are implemented and how your data structure works. If it works like a stack, it's a stack. And if it works like a queue, it's a queue. Okay, it doesn't matter how you code these things. All right. All right, so how does a stack work? That's what we got to learn. So probably almost all the books up here on the shelf, and if you look online, when you look up what a stack is, they'll usually describe it as a stack of paper or a stack of books, or a lot of times they'll say in the cafeteria they have the trays stacked up. Okay, they always give that kind of example of cafeteria trays for some reason. But you can kind of visualize that in your head. That's a stack. Okay. It allows access only to the last item inserted. So in other words, you can only pull things off the top of the stack. What happens if you try to pull something out of the middle of the stack? Yeah, it topples over. So you're not allowed to do that. So with a stack inside a stack data structure, you can only remove things, and it's called popping things off the stack. So when you remove an item from a stack, it's always from the top of the stack, and it's called popping it off the stack. Okay? When you're putting things onto a stack, guess where you get to put things? You can't put things in the middle of the stack. You can't put things on the bottom. Yeah, you always have to put things on the top of the stack. And when you put things onto the top of the stack, it's called pushing things onto the stack. So you always push to the top and you pop from the top. Push to the top, pop from the top. Okay? So you have your push operation and your pop operation. Okay, most places will expect you to know what LIFO means. Okay, if they ask you for a LIFO data structure, you should think of stack. Okay, or if they say, hey, is stack a LIFO or a FIFO, hopefully you know, oh, okay, LIFO data structure. Okay, and LIFO stands for last in, first out. Okay, so the last item you put in is the first item you're going to take out. So that's a LIFO type data structure. Okay. Cool. Where are stacks used? To parse arithmetic expressions. In fact, I can't remember if this book has the arithmetic expression. By the CPU to execute instructions, we've come in contact with that, and used in other data structures like binary trees, and you can even make a queue out of a stack. Another example would be a compiler to parse a text file, and we're actually our piece of a compiler to parse a text file, and that's what we're going to write today, a piece of the compiler. Okay. All right. Take a look at a stack. I'm not going to use my applets. I've kind of just said, hey, I'm not going to use this. So let's look at our code. So first, before we look at the code, let's look at the 5 functions that are implemented in a stack. Of course, we have the push operation I already told you about. It puts things into the stack on the top of the stack. Pop takes an item off the stack and removes it from the stack. Peek lets you look at the top item on the stack. So it lets you look at the stack, but you're not actually taking it off the stack. Just looking at it. And you can only look at the top one. Is full checks to see if your stack is full, and guess what is empty does? Checks to see if your stack is empty. Okay. Alright, let's look at our code. In fact, I gave you guys the code. So we have a stack app right here. So if you guys wanted to run, actually you guys will need this code today because you are going to have a class assignment dealing with this code, but you can download it in a second also. Alright, remember the easiest way to kind of get these classes in here is just to make a new class and then copy and paste it. As we're looking at this code, I'm going to do our visual in Excel here. And this stack has lots of the stack code has lots of comments. It did not indent well, so you can do Control A, Control I to indent it. Here is some stack code. Notice it's nice and short and very easy to read. Stacks are created very simplistic because they are just a simplistic data structure. They want to be closer to the hardware, so you don't want a lot of confusing code in here, right? That's why we use stacks. So remember, you can implement stacks different ways. You don't have to always use an array. This code here uses an array to implement the stack. You can use a linked list to implement a stack. Okay? You can kind of think how you could use a linked list to implement a stack. But because this is using an array, now many times, even if they use a linked list, we'll draw a picture of our stack. And remember that when we're dealing with a lot of these data structures and these algorithms, we have to visualize, right? We have to visualize what our stack looks like. And oftentimes they'll draw a stack and they'll make it look like this. They'll draw the array up this way, and so that, you know, you start with your 0 index at the bottom and it goes up to the top of the array. Now you can think of it as an array or a linked list, but this is a picture of our stack. So oftentimes they draw stacks and they make them look like this picture. Okay? It's an easy way to kind of visualize a stack. Whenever I visualize a stack, maybe because stacks, you know, pile of papers, pile of memory locations. Same thing. All right. So there's our picture of our stack. Note how we're going to implement our stack with these 3 instance variables inside of this code's implementation. In this code's implementation, we're going to have a stack of type long values, because that's the way that this person wrote their code. This was actually came with the old LaFour book. Okay. And he used an array to implement his stack. So in this code, they used an array to implement it. He has another instance variable called max size, so that because he's using an array, he has a max size. Note if you implemented a stack with a linked list, you would not have a max size, right? Yeah, if you use a linked list, remember linked lists can grow infinitely, and so you wouldn't need a max size, unless for some reason you wanted another max size. But because we're using an array, we can't go out of the bounds of the array, we have to keep track. So use that max size. And then importantly, even if you use a linked list or an array, you have to keep track of who's on the top of your stack. Okay. So in this implementation, top is going to be the index in our array of who's on the top of the stack. Okay. If we used a linked list, you could think, okay, that would be my head pointer would be the top of my stack. So in this implementation, we use an integer because he's going to be the index in the array of who's on top of the stack. Okay. So no matter how you implement these things, you do have to keep track of the top of your stack, either with a head pointer or a head node pointer or with an integer. Okay. All right. So in this implementation, here's our constructor. We initialize our stack with a certain size, so we say how big we want our stack. It creates that array, that size, and then top is initialized to -1. And you might think, well, why is top initialized to -1 at first? But when we look at the rest of the code, you'll see why he is. So I'm going to make my little top pointer down here. And right now he's pointing to -1. So you can kind of think he's not pointing anywhere in the array. You can kind of think that he's pointing to underneath the array. He's not really pointing anywhere because you can't index an array at -1, right? We'll get an index out of bounds error. Okay, so right now he's just -1. And that was our instantiation of our stack. That's how he'll be constructed. All right. How do we add something to a stack? Well, we call push. Here's our push operation. 1 line of code. Very nice. Very easy to understand. Okay. So when we put an item on top of the stack, we send it what item we want to push onto the stack. And since we're having a stack of long values, we're pushing in a long. Okay. Note that we have a pre-increment operator. You guys remember the difference, hopefully, between a pre-increment and a post-increment? Pre-increment, we add 1 first, then use the variable. Okay? So when we're adding things into our stack, it'll call this function push. It'll add 1 to top, and then put that new item in that array at index top. So when we're adding the first item, will it work? Yes. Because remember your order of operations. The pre-increment operator says add 1 to top, so -1 plus 1 is 0. So he's going to point here to 0 now. Okay. And then put the item J, whatever it is, maybe like the number 59, at that index location, so it pushes it into our stack. Okay. So it pushed it into our stack. Back, let's So these are indexes, remember. These are our memory locations. I'm just going to make them a different color. So then they look more like something different. All right, so we understand the code for pushing in something into a stack. This is why I like stacks, so easy. Okay, popping something from a stack. Here we have the post-decrement operator. Remember, any kind of post-decrement operator happens after we use top. Okay, so what happens when we pop something from the stack? It returns whatever top index is, then subtracts 1 from top. So it uses top first, whatever he is. So right now, top is equal to 0. So if I were to pop 59 from the stack, it would go to stack array 0, return that number 59, and then minus 1 from top. Because that's what the post-decrement operator does. It does it after it uses top. Okay? So it would return 59 to me, and then it would make top back to -1. Okay? Now, is 59 really gone from my array? In memory, he's still there, but in the stack, he is gone, because next time I go to insert something in the stack, where is it going to insert it? At index 0, it is going to overwrite the 59. Okay, so when you're popping something from the stack, physically in memory, the ones and zeros are still there, but abstractly for the stack, it is not there anymore. Okay, so 59 is pretty much gone. In fact, a lot of times you draw your picture, they go away. Okay, when you pop something from the stack. When you peek at your stack. Actually, this one will throw a runtime error if our stack is empty, so we have to remember to check if it's, they'll do an array out of bounds error if he's empty. Can you guys see if he's empty? He's going to do an array out of bounds error because he's going to go to -1. So we only want to do peek if there's stuff in our stack. Okay. Notice that peek doesn't remove him, but he just gives us whatever's at the top. He returns it to us. Is empty, all it does is do a check. Hey, if you're -1, then we're empty. If top's -1, that means there's nothing in the stack. If that index is -1, right? And then is full, before I even get to that code is full, what should it be? It returns top equal. What would be the code right here? Going to return top equal. How do you know you're full? Huh? Yeah, the max size. If you equal max size or your array.length. Okay? So in this implementation, we can tell if we're full if we equal our max size -1 because our index, remember top's an index, or array.length -1. Okay. All right, that's it. That's our stack. Pretty sweet. All right. If we were to run some code like this, it's good to have a visual of what's going on. In fact, on your test and things, we give you this code. We say, draw a picture of your stack. You should be able to draw this picture of your stack. Okay. So what happens when we push something into the stack? So note, well, before we even push anything into the stack, note that our stack is length 10, so I actually drew a picture of our stack over there. He is 10 elements long. So that's a picture of our stack, 10 elements with indices 0 through 9 because we're using an array. And then the stack.push, where does he push him onto the stack? Yeah, the top of our stack. Remember that he increments the top pointer or index, and then he pushes that value onto our stack. That's this line of code right here. When he gets to this line of code, what happens? So remember what this code looks like? It increments top and then puts it into the array. So Remember, he increments top and then puts that value into the array. Okay. Same thing here. We push another value, it increments top, pushes that value into the array. Last one, increments top, pushes that value into the array. All right, here we have a while loop. While not the stack is empty, so while the stack is not empty, so while that's returning false, that means keep this while loop going while we have false for the is empty, so while he's not empty. And what are we doing in this loop? We're just popping things off our stack. Okay. Alright, so remember that when we pop things off our stack, just kind of a review. He goes to top. He pops this guy off the stack, so he's abstractly gone. He returns him to the program. And then he decrements top. So this would be our return value, right? And if we pop the next value, he pops whatever's at index 2. So he's abstractly gone. He returns that value, and then he decrements top. Pretty easy, right? Awesome. That's a stack. That's all there is to it. Any questions on stack, actually? I'm going to assume everybody knows what a stack is. Okay, let's look at Q, and then we'll come back to that parser stuff. So whenever we talk about stacks, usually that same chapter in all these books talk about queues because they're the same type of abstract data types. They're used as compiler tools also. They're used kind of in the same way. Their code looks very similar to each other. Okay. When you draw abstract pictures, it looks almost the same. So they're, they're kind of always lumped together. You guys might have, now when I was going to college, nobody knew what Q is, but now people actually use the word Q in normal language, right? I've heard it said a few times. When you're waiting in line somewhere, they'll say, oh, go wait in the queue. Or when you're on a phone, for like help service, they'll say, oh, you're 5th in the queue. Right? So a queue you can just kind of think of as a line of people, waiting for something, right? A lot of these books always say waiting at a movie theater for some reason, I don't know. But it's just a line of people like waiting. You can think of that as kind of like your queue. Okay? It's a line or sequence of people or vehicles awaiting their turn to be attended to or to proceed. A list of data items, commands stored so as to be retrievable in a definite order, usually the order of insertion. You can think of your programming lines of code as a queue to be executed by your CPU. Queue of instructions. Right? Lots of queues are used underneath inside of your compiler, inside of your operating system. So remember that stacks are a LIFO data structure, last in, first out. Queues are a FIFO data structure. So if they ask you FIFO, it means first in, first out. Okay. Queues are usually described with these 5 methods. They have an insert method, a remove method, an is empty, is full, and a size method. Okay. Let's look at them. We didn't do that. So let's look at the code. Actually, I gave you guys the code here. We'll look at our Q code. So here's our Q app. It's nice, easy code. Very user-friendly. I think I called him Q app. And a lot of times when we make cues, we think of them kind of the same way. You know, we picture them or visualize them as kind of like a stack. Usually they'll draw it like this. Sometimes you'll see cues drawn, you know, horizontally. A lot of times you'll see cues drawn vertically. Okay? But they're usually drawn very similar to what a stack looks like. So when you get that visual, just think of a lineup. You can think of it kind of as an array. Alright? Alright, so let's look at our instance variables for our cue. So remember that you can implement a cue different ways. You can implement a cue with a stack. You can implement a cue, actually not with a stack, with a linked list. You can implement a cue with nodes. You can implement a cue with an array. In this code, they chose an array to implement their cue. All right. So when you implement an array with or a cue with an array, you have to keep track of that max size for the same reason, so you don't have an array out of bounds error. Okay, remember, if you implement a cue with a linked list, you have an infinite size. Some things that you want to keep track of in your cue is they need to have a pointer called the front. Now note, inside of this implementation, this pointer is going to be an index in our array, so it's going to keep track of the index of the front of our cue. And then we're going to keep track of the index of the rear of our cue, the last person in the queue. Why do we need to know where the last guy is in a queue? You think why you need to know where the end of the line is? If you're going to go line up at a movie theater, do you need to know where the end of the line is? Sorry, Justin? So you know how big it is, for one. Yeah, know where to line up. Know where the next thing goes. So if you're going to go line up at a movie theater, you need to know where the end of the line is so you can get in line. So same thing here. If you want to insert something inside of your queue, you need to know where the end is so you can insert something in the end. Okay, so you have to keep track not only of the front, but of the end, the rear. Unlike a stack, you only have to keep track of the top. But a queue, you know, you're removing things and adding things in a queue, it's going to be a little bit more movement in our queue. Okay? And you always have to add things at the rear of a queue. That's the rules. That's how a queue works. You can't change the rules of a queue or else it won't be a queue anymore. Okay? All right. And then it's good to keep track of the number of items. In this implementation, it's good to keep track of the number of items so we don't have an array out of bounds error. Okay? Alright. So in our queue constructor, so when we instantiate a queue, we tell it how big we want our queue. We initialize that array. Our front pointer is actually 0 and our rear pointer is -1. So we can write that into our visual here. And our number of items is 0. Okay? So our front pointer, we're not going to have top anymore. We have an index, or we have an int that keeps track of the index in our queue called front. And if we implemented it with a linked list, this would be a node pointer, right? Here's the front of our queue is at index 0. In fact, let's delete these things from our queue now. This is going to be our queue now. Our rear is at -1. Our number of items is 0. And that's our array. Let's look at our methods for our queue. Here's our insert and remove method. It's more than one line of code, but not that much harder. Okay. So note that this queue actually checks to see if the rear equals max size -1. What does that mean? It's not full necessarily. If the rear equals max size -1, so let's say our size of our array is 10. If he equals max size -1, where does it move him? Back down to -1. And you're going to see something cool in this queue. It actually wraps around. It actually, the front sometimes can be, you always have the front of your queue, but as your queue, is moving, it actually will start wrapping around the array. Okay? The way that they implemented it. All right. we'll add some things in a second. Here's our Q array. It says plus plus rear. So remember that's our pre-increment operator. So it happens before we use rear. So same kind of methodology here. It adds 1 to rear and then inserts the item at that index. So if rear starts out at -1, the first item will be inserted at index 0. And then number of items plus plus. So it keeps track of the number of items. All right. When we remove something from the queue, we use that post increment operator. So remember, when we're removing something from the queue, let's assume that we inserted something, right? Rear came up here, we inserted, let's say, we're inserting longs, so we'll insert the number 45. When we're removing something from the queue, what does it do? It takes wherever front is pointing, so front's at index 0, it takes that 45 and puts it into temp. So it has a little temp holder over here. And he's holding that value 45. And then what does it do to front? It says front plus plus. So it actually increments front. Okay. If front equals max size, front equals 0. That's where we get the wraparound. Okay, if you ever get to the end of your queue, we'll add enough stuff that we'll get to the end of our queue, you go back down to 0. Okay. All right. Number of items minus minus because we just removed something, and then we have to return that temp because that's what we just removed. Okay. Peak front just tells you what's in the front. Is empty, just checks to see, hey, number of items equals 0. That's pretty easy to understand. And is full, number of items would equal max size. And of course, size just returns the number of items. Those are pretty easy. All right. Let's do this code right here so we can understand it better. And they made a queue of 5, which is probably a good idea. So then we're not standing here inserting things forever. So we'll make our array length 5 the same. Let's get rid of this. We'll put temp over here. Remember that in our constructor, front starts out at index 0 and then rear starts out. That magnifying glass is getting in the way. Go over here. There we go. All right. Does that look okay? So remember in our constructor how this thing starts out. If we give it a size 5, it'll make an array from 0 to 4. Front starts out at 0, rear starts out at -1, number of items is 0. All right. Let's run this code now. So we're going to insert 10, insert 20, insert 30, and insert 40. So let's look at our insert and make it work. Obviously, rear doesn't equal max size -1. We don't have to worry about that if statement. Okay. Q array plus plus rear equals J. So we add 1 to rear. We add 1 to rear. And then we are inserting the number 10, right? So we gave it as that J was equal to 10, because that's our parameter. And we gave it the 10 as the argument, so we insert that 10. Voila, he's right there. Okay. What if we insert something else? We run this code again. This is obviously going to be false. It comes here, rear plus plus, and then insert J. Rear plus plus. Rear becomes index 1. We insert the 20. What happens if we insert 30? Rear plus plus, we insert the 30. What happens when we insert 40? Rear plus plus, we insert the 40. You see how your cue is working? Yeah, he's pointing to the first thing. The front is pointing to the first guy who got inserted. Rear is pointing to the last guy who got inserted. Okay. What happens, let's just assume that we're trying to insert a couple more items. What happens if rear, we insert, let's say, the number 50 here, and then we try to insert the number 60, what will happen right here? Actually, this one doesn't check to see if he's full. Okay, scratch that idea. We don't have to go to check if he's full. We'll have to check if he's full down in main. Okay. So we'll leave it like that. Sorry, shouldn't deviate. All right, so we inserted 10, 20, 30, 40. That's what our cue looks like in RAM, right? That's how we're visualizing. And then it says remove, remove, remove. So let's remove some items. Let's go to our code to see how remove works, right? How do we remove items? We say, okay, go to the front index, take that value at front index, store it in temp, and then add 1 to front. Okay, so temp's over here. He'll take whatever value is inside of that index at 0, because that's where front is, front's 0. And then it says increment front. See how that worked? And then it returns number of items minus minus, and then it returns that temp. So it returns temp. What happens when we remove it? I know in memory it's still there, but in essence it's deleted. Okay, so when we draw pictures of it, we pretty much just cross out the 10. He's no longer there. Okay. When we insert something else, or we remove something else, we come to this code again. It takes whatever's inside of the front index, puts it in temp, or front plus plus. This guy is now gone. And in the code, he does it one more time. He removes another item. Front becomes, oops, dang it, I skipped ahead. We take whatever's inside of this index, we put it into temp. Front then increments. And so this guy's pretty much gone. Okay, so that's the visual you should have when you look at that code. Okay, there's one item in our queue, and front and rear are both pointing to it. When we get to this point in our code. All right, let's look at the wraparound. So we're going to insert 50, 60, 70, and 80. Okay, so let's see how that wraparound kind of works. So if we go to insert here, hopefully you guys can visualize this. What happens? It says plus plus rear. So we increment rear first and then insert the item. Now we're going to insert 60. What happens now when we try to insert 60? Right. The if statement becomes true and rear becomes -1. So note that when rear is at the top of our array, he's going to equal max size -1. This is where we get that wraparound. Rear then jumps to -1 again, goes back down to the bottom, and then we add 1 to rear, just like before, and we insert that item where rear is. And then we had to insert 70 and 80. So rear is not going to wrap around anymore. That's going to be false. He'll insert 70. And then he'll insert 80. Actually, did he insert 80? I think he did. Yeah. Okay, so note in this instance, or this example, front is actually, looks like it's in front of rear, but he's really not, right? Front, well actually, not it looks like behind rear, but he's really in front, right? Yeah. All right. So is Q's making sense? I won't go through all the removes again. You guys can visualize that. Okay. All right. Any questions on Q's? Q's pretty easy. Nice, friendly data structure. All right. Awesome. You definitely will come in contact with stacks and queues in your lifetimes, right? Especially if you're a programmer. Let's go over our class assignment, what you're going to do. So, for this class assignment, we are going to make part of a compiler, which is kind of fun. We're going to use our stack code, and we're going to make a program that checks to see if every curly bracket, so forward-facing or open curly bracket, is matched to a closing curly bracket. Checks to see if an opening parenthesis is matched to a closing parenthesis. And last, checks to see if every square bracket is matched to a closing square bracket. So we're making a parser to be a bracket checker. I bet all of you have come in contact with the compiler when it's yelling at you that you're missing a bracket. It's running code like this. It's using a stack to parse it. Okay? So for example, just so we know we're all on the same page, let's look at these examples. If I inserted some string that looks like this, it would tell me it's correct because this bracket matches that bracket. Square bracket, square bracket. If I inserted a string that looks like this, it would say it's correct because I have opening curly bracket, open square bracket, closing square bracket, closing curly bracket. It all matches. These last two are incorrect because we have an opening curly bracket, opening parenthesis, closing square bracket does not match the parenthesis. So that's where we get our error, right? And then opening curly bracket, opening square bracket, close square bracket, close curly bracket, and then we have an extra bracket in here, so it should throw an error. Okay? As the string is read, each opening delimiter, so this is how we're going to implement this thing. So as you're parsing your string and you're reading each character from your string, every time you get to an opening delimiter or an opening bracket, right, you're going to put it or push it onto the stack. So you're going to push all your opening curly brackets, square brackets, parentheses onto the stack. Now every time you reach a closing delimiter or closing bracket, you're going to pop something from the stack and see if they match. And if they match, then all is well. If they don't match, then you know something's wrong. If all their characters are ignored, and then when you end, if something is left on the stack, you know there's an error as well. Okay? So here's a kind of a visual of how the stack is going to look. So let's say we're reading in a string that looks like this. A, opening curly bracket, B, opening parenthesis, C, opening square bracket, D, okay. So we're reading in these characters one at a time. When we reach an A, we don't push anything onto the stack. When we reach an opening curly bracket, we push it onto the stack. B, we ignore. That's what our stack looks like. When we get to an opening parenthesis, we push it onto our stack. So our stack is just turned sideways here in this picture, right? The horizontal stack. When we reach a C, we ignore it. Opening bracket, push it onto the stack. When we reach the closing curly bracket, we pop this guy off the stack. Make sure they match. E, we ignore. When we get to the closing parenthesis, we pop this off the stack. Make sure they match. And then last but not least, when we get to our closing curly bracket, we pop that guy off the stack and make sure they match. And then one step I did leave out of this, but it was in one of our examples, is if there's anything left on the stack at this point, we know we have an error. Yeah, if there's any opening curly brackets left on the stack, we know, hey, there's an extra closing bracket. You guys ready to code this thing? Now you can code it as programming pairs or by yourself. And I'm going to have you guys program this as a class assignment. You can use our stack code that we just downloaded and that we just examined. So we'll want to use that stack app code. You'll have to change your stack so that it can house characters. So right now our stack, in fact I'll help you change this code. It's not very hard. It's pretty simple. Notice that our stack array is going to be a stack of longs, and we want to push characters into the stack. We want to push those brackets into our stack. So this should be pretty rudimentary to change this guy to a character stack, right? Now everywhere there's a red underline, it probably has to be changed to character. So we need to instantiate, or initialize, a character array. We need to push in characters, and we need to pop out characters. When we peek, we need to peek characters. And is empty and is full is okay. Now main, we're going to change. So I'm not going to have any of this guys in main. We can keep main here because you guys can just write this in main, it's fine. Alright. So you can create another method if you want. You'll create that method here inside of the class, not in your stack. You don't want to change your stack code any more than we have already. You just want to make it a character stack. Leave your stack code alone. Don't add methods to your stack. Your stack is your little robot object. Don't add methods to your stack. If you want to write an extra method to help you out, write it inside this class stack app. Okay? Or just put stuff in main. I don't mind if you write this one all in main if you want. Okay? It's part of the compiler. So you'll have a string, we'll have a test string. This is our test string. Remember that your test string will have some brackets in it. You can have some letters in it. You can have some more brackets in it. Brackets separated by letters. Remember that doesn't have to have just one letter. And it should test all kinds of brackets. Okay? It doesn't matter how many letters, because remember that it ignores the letters. In fact, it'll ignore white space too. White space is a character. Now you can do a simpler test string at first, but it should work for any type of test string. Is that one correct or incorrect? I made a really weird one. Yeah, it is correct. It should be correct. I meant it to be correct. I think it is. Okay? So all the opening curly brackets have a matching closing bracket. Now note too, like if I put it, if I mix up, let's say the square bracket with the parenthesis, it should give an error, right? Because they have to be in the correct order of closing curly bracket or closing brackets as well, right? So that one would throw an error because it wants a matching square bracket here and it gets the parentheses. So that would throw me an error. Alright. So first things first, we need to create our stack, right? So hopefully you guys know how to create a stack. So we just make a stack. You can kind of use, this code down here, even, copy and paste it. Alright. And then you guys will use a for loop, right, to convert your string into characters and push them onto your stack. And actually we can make a stack bigger than 10. Let's make it at least, well actually we're not going to use that much, but whatever. Go ahead and make this guy. Note that the stack has a max size, but it doesn't give me an accessor, so I went ahead and just made this size down here. All right. So we're going to push. Now note that we have to push a character onto the stack. So that will fill up our stack with all of our characters. Now we don't want to fill up with all of our characters. Okay, I just wrote this code to kind of give you an example of what you got to do. We don't want to push all the characters. Now this would push all the characters in that string onto the stack. We don't want to do that. What do you guys want to do? We want to pull out the character. In fact, we can write our algorithm here. Maybe it'll help us if we write our algorithm out together. So the things that we want to do inside of this for loop, what's our steps? Kind of deviated from writing these. What's our first step? We need to pull a character out of the test string, right? In fact, we can even make this a more formal algorithm. We can say for 0 to num of, or you can even put test string dot length. Pull a character out of the test string, then you want to check to see if that character is a opening parenthesis, an opening curly bracket, or a square bracket, right? Then what do you guys want to do with it? Push it on the stack. What if it's not an opening curly bracket, square bracket, parenthesis? You don't have to do anything. Alright? So only if it's, an opening parenthesis, opening curly bracket, opening square bracket, you push onto the stack. If it's not, and if it's just a regular character, then we ignore it. Now what's the other character we have to check for? Closing curly bracket, closing parenthesis, closing square bracket. Okay, so we can say else check to see if that character is a closing parenthesis, closing curly bracket, or a closing square bracket. And if it is, then we want to do something else. What do we want to do? If it's one of the closing ones, we want to, you guys tell me. I don't want to write the whole thing by myself. Not push on the stack, we want to. If it's a closing one, we want to. Yeah, we want to pop whatever's on the top of the stack and see if they match. Remember, whenever you come in contact with a closing one, on the top of the stack should be his buddy, his matching buddy. Okay? Alright. So if it is, pop a character off the stack. And check to So what you just popped off the stack. Check to see if your character, that current character, matches the opening bracket that you just popped off the stack. Maybe I'll just say opening bracket. Okay. Okay, so if it is, then everything's well. What if it's not? Then so now we're checking if it's not that. What do we want to do if it's not the right bracket? Tell them, hey, that's an error. Stop your program from running. Break out of it. Do something. Okay, right? It means there's an error. Okay? So we can say send error report. You guys could decide what to do right there. But pretty much there's an error. I'll just put then there is an error in our string. Otherwise, you go on to the next character. Otherwise, all is well. Okay, note that we don't have to check if the character is a letter. We don't have to check if the character is a number. We just have to check when it's a bracket. Okay? Now, if we reach the end and we haven't left, and we should put in here, end our program right here, actually. You guys can decide how to end your program. But if we come out of that for loop, so you'll reach the end of the for loop. With no errors, right? So what does that tell us if we reach the end of the for loop with no errors? Your string is correct. So you'll output correct, all is well, and that'll be the end of your program. So I kind of did a mix of formal algorithm and just plain old English. So hopefully that's a good algorithm. Whenever I write algorithms for myself, that's how I write them, actually. Okay, we try to put the keywords capitalized, so then we know where we need to put our programming constructs, right? The if statements and the for loops and the do's. And all right. Cool. Now you guys got the algorithm. We changed your stack so it houses characters. You should be able to knock this out in 10 minutes, right? All right. So not that hard. Remember that you can work in programming pairs or you can work on your own. All right. Any questions on this? Otherwise, I will stop recording here and let you guys work. Cool.